Yo, what's up YouTube? Welcome back to Intuition. In today's video, we're going to be covering some more advanced math topics. Today we're going to be learning how to diagonalize a matrix. We're not only going to be learning how to diagonalize a matrix, but we're going to be learning what it means, and we're going to be applying it to solve a physical problem. All right, so let's hop right into it. Okay, the problem that we're going to solve today is going to be a problem that we've already covered on this channel. We're going to be using matrix diagonalization to once again go over the topic of minimum, maximum, or saddle point of a function. So let's go over that again. A minimum point is a stationary point, which means that the slope at that point is flat, which means that the first order derivative goes to 0 at that point. And as you move away from that point, the function increases, or the function expands as you move away from that point, and it expands in all directions. That would be a minimum point. And another type of stationary point is a maximum point. Once again, the slope is flat at that point, but the function decreases as you move away from that point, because that point is a maximum point. And then we have saddle point. A saddle point is different from a minimum and maximum point in that the slope is still flat at that point, but the thing with a saddle point is that the function increases as you move away in one direction, and then it decreases as you move away from that point in the opposite direction. Now you might wonder, what does all this have to do with matrix diagonalization? Well, let's go ahead and analyze this some more. When it comes to figuring out what type of stationary point you have to take a look at this expression here, which comes from the Taylor series, which allows us to approximate how a function behaves near a certain point. So these are the second order derivatives of a Taylor series, which allows us to analyze the curvature of a function at a certain point. All we need to do is analyze whether or not this expression is positive definite. If it's positive definite, that point is going to be a minimum point. If it's negative definite, it's a maximum. And if the function increases in one direction, but decreases in the opposite direction, then that's going to be a saddle point. So this should be a straightforward problem for us to figure out. The issue with this is this mixed term here in the middle. This mixed term here in the middle has a delta x times a delta y. And the issue with this mixed term is that delta x could be positive or negative, and delta y could be positive or negative. Whereas for the first term, all we need to do is look at the f sub xx, right? The same thing with the last term, which is f sub y times delta y squared. Delta y is being squared, and all we need to know is whether or not f sub y is positive or negative, but this middle term here does not give us that luxury. So now the question is, what causes this mixed partial derivative to be a factor in curvature? Well, this occurs when our coordinate system does not line up with the symmetry of the function at that point. If our coordinate system looks like this and doesn't line up with the symmetry of the function at that point, then we're going to get these mixed partial derivatives. So what can we do about that? Well, remember, coordinate system is arbitrary. We can choose whatever coordinate system we like. So we can choose a more convenient coordinate system, which means that we can move away from this coordinate system that we have here and rotate it so that we have new coordinates that line up with the symmetry of the function. And when we do that, we can express this curvature in our new coordinate system. So we're going to change from xy coordinates to uv coordinates. And when we do that, our mixed partial derivatives vanish. And now this expression is easier to analyze because all we have to do is look at f sub uu and f sub vv. We just need to rotate our coordinate system to line up with the symmetry of the function. And this is going to entail diagonalizing the matrix. So let's go ahead and take a look at what we mean by that. So remember, this is the expression that we're trying to analyze. And what we're going to do is we're going to write it in matrix form. So writing it in a matrix form, it's going to look like this. Now you should be familiar with how to multiply matrix. It's just the rows of the matrix on the left times the columns of the matrix on the right? It's just rows times columns. So this is what the curvature looks like in matrix form. And this matrix here in the middle, this 2 by 2 matrix, we're going to call that our curvature matrix. So what we want to do is we want to change the coordinate system from xy to uv. And when we do that, our curvature matrix is going to become diagonalized because the mixed terms are going to vanish. Off diagonal terms are going to vanish. And that's exactly what we want. Okay, so how do we do that? So the way that we do that is we express u in xy coordinates. Delta u in xy coordinates will be delta u sub x and delta u sub y. And we multiply our curvature matrix times our u vector. And now, since u is an axis of symmetry, when we multiply our curvature matrix times our u vector, we should get back the same vector. So which means that our curvature matrix should no longer mix our u vector with the v vector, because that is an axis of symmetry. We should get back the same vector, and this vector is just going to be rescaled. So it's just going to be multiplied by some constant called lambda 1. We simply get f sub uu, which is what lambda 1 is going to be equal to, and it's going to be multiplied times the u vector. And likewise, when we apply our curvature matrix to our v vector, which is going to be another axis of symmetry, we get lambda 2, which is another constant, times the same vector. And lambda 2 is going to be equal to f sub vv, which is the second order partial derivative in the v direction. And when we have done this, we have officially diagonalized our matrix. We're only going to be left with our diagonal terms, which is going to be lambda 1 and lambda 2. This is what our curvature matrix is going to look like when we change our coordinates to uv coordinates. So that should make sense. All right, let's continue. Lambda 1 and lambda 2, these are what are going to be called eigenvalues. So we're trying to solve for the eigenvalues of the matrix. Here's the expression that we're trying to solve for. And what we can do is we can subtract lambda 1 times the u vector from both sides. And when we do that, we get our curvature matrix minus lambda in parentheses times our u vector. And all of that is going to be equal to 0. Inside the parentheses, we have a matrix minus a scalar. The scalar is basically being multiplied by the identity matrix, which simply means that we just have to subtract the scalar from the diagonal terms of the matrix. So the diagonal terms of our matrix are going to be f sub xx minus lambda 1 and f sub yy minus lambda 1. Now, how do we solve this equation? We have a matrix times a vector equals 0. In order for us to get a non-trivial solution, we need to set the determinant of the matrix equal to 0. And the determinant of a 2x2 matrix is simply the difference between the cross products. And we characterize our determinant by getting rid of the brackets and put in vertical segments. One cross product is going to be f sub xx minus lambda times f sub yy minus lambda minus the opposite cross product, which is going to be f sub xy squared. This is the determinant, and we set this equal to 0. And when we expand this expression, we get a second order polynomial of lambda. This is a quadratic equation of lambda. And you guys should already know from your algebra class, when you have a quadratic equation, you should get two solutions. And these two solutions are going to be our lambda 1 and our lambda 2, which are our eigenvalues. And these are going to be the terms that we put on the diagonals of our matrix. Okay, so let's go ahead and apply what we just learned to a specific problem. Okay, this problem says the second order derivatives at a stationary point are as follows. F sub xx equals 4, f sub xy equals radical 7, and f sub yy equals negative 2. What type of stationary point do these derivatives represent? Use matrix diagonalization. And through what angle must we rotate our xy coordinate system to diagonalize the curvature matrix? Okay, let's get to work. So we just go ahead and plug in our second order derivatives to see what the quadratic equation looks like. And when we do that, we get lambda squared minus 2 lambda minus 15 equals 0. We can go ahead and factor this polynomial, and it factors into lambda minus 5 times lambda plus 3 equals 0. And therefore, our eigenvalues are going to be lambda 1, and it doesn't matter which one you call lambda 1 or lambda 2. We're going to call lambda 1 equals 5, and lambda 2 is going to be equal to negative 3. So these are the eigenvalues. So we have officially diagonalized our matrix, and we have the diagonals of 5 and negative 3, which means that in the u direction, the function increases, but in the v direction, the function decreases, right? This is clearly a saddle point. And now we just need to figure out how we rotated the xy coordinates to get our uv coordinates. How much rotation did it take for us to change from one coordinate system to the other? All right, so let's go ahead and figure that out. So since we have solved for our lambdas, we can go back to the expression that we started with, which was this 2x2 matrix times our vector u or v. We'll start off with vector u. So this 2x2 matrix times our vector u equals 0. And now we can go ahead and plug in 5 for lambda 1 and plug in our second order derivatives into this matrix. And when we do that, the matrix becomes negative 1, radical 7, negative 7. Okay, so let's go ahead and multiply this matrix times our u vector. And when we do that, we get this expression. Row 1 is negative delta u sub x plus 7 delta u sub y. If you simply multiply row 1 times negative radical 7, you'll get the same expression in the second row. So row 1 and row 2 are identical and they equal 0. We just want to know in what direction does our u vector point. To figure that out, all we need to do is get the slope, and the slope of the vector is the y coordinate divided by the x coordinate. The slope is the rise over run, the y coordinate over the x coordinate. So we have delta u sub y divided by delta u sub x, and that's going to be equal to 1 over radical 7. All right, so 1 over radical 7 is going to be the slope. And how do we get the angle from the slope? The angle is simply the inverse tangent of the slope. So we take the inverse tangent of the slope, and that should give us the angle. We take the inverse tangent of 1 over radical 7, we get an angle of 20.7 degrees. All right, so we got our answers. We have a saddle point, and we diagonalize our matrix by rotating our coordinate system by 20.7 degrees. Easy. All right, so there you have it. Let me know if that was helpful. If you guys have any questions, go ahead and leave it in the comment section below. Continue to look out for our videos every week, and I appreciate you guys for watching. With that said, I'll see you in the next one. All right, bye-bye.